Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 6, Lesson 10, Modeling with Inequalities. So for the last two lessons, we've actually looked at solving two-step inequalities. Now remember, you solve a two-step inequality exactly like you solve a two-step equation, with that one exception that we saw in the last lesson, that if you multiply or divide both sides of an inequality by a negative number, you have to flip the direction of an inequality. So if it was greater than and you divide both sides by -2, suddenly it becomes less than, and vice versa. Today what we're going to be doing is we're going to be looking at a lot of different real-world scenarios that can be modeled using two-step inequalities, and then we're going to solve those inequalities to find out values that, solve the real-world problem that we're looking at. Let's get right into it. Now, that being said, some of the problems that we're going to do today, it's going to be nice to have your calculator on. So I would suggest having one handy just for doing some simple arithmetic that I don't really want to have to do longhand on the side of the paper. All right, let's do it and jump right into exercise number 1. Many real-world situations can be modeled using two-step inequalities. Just be careful to read each problem. All right, exercise number 1. Rosa is putting money into a savings bank she keeps at home in order to save up for a digital camera. She starts to put $20 per week into a bank account, which started with $60 already in it. She wants to save at least $400. Letter A asks, will 12 weeks be enough time? Show the calculations that lead to your answer. All right, now I've highlighted the word at least here because that is a huge indicator that there's an inequality out there. And it could be, think about this, right? You may have wanted to purchase something in the past, a camera, a bicycle, a phone, right? And maybe there's some phone, let's go with that one, that is, the least expensive that you want to get. Maybe $400, right? But maybe there's some phones out there that are they're really nice, $700, $800 phones. So, you got to save up at least $400, but you could also save up $600, $700, $800, right, to buy those more expensive phones. That's what's going on right now. Now, we need to figure out, will 12 weeks be enough given that Rosa is putting in $20 per week, right? There's a nice rate, right? $20 per week, and she's starting with $60. We don't want to forget that. She's not starting from nothing, all right? So, will 12 weeks be long enough? Why don't you pause the video right now and figure out whether 12 weeks will be long enough for her to save up at least $400. All right, well, how would I do this? Well, I would likely take, my 12 weeks or my $20 per week. I might multiply it by 12, and then I should add on that $60, right? I could do this all at once on my calculator, or I could just kind of, do it longhand. So 20 times 12 is going to be 240, all right? Then I'm going to add on another 60, and that's going to be $300, all right? So I've got 12 weeks times $20 per week, right? That's $240, plus another 60 gives me $300. She needs to make at least $400 in order to buy, right, a digital camera, so the answer is no, right? And this problem's a good one just to kind of get a basis for understanding what the phrase at least means, She's got to have, the least amount she could have is 400, and after 12 weeks, she's only saved up 300. Let's take a look at letter B. If n represents the number of weeks Rosa has been saving, write an expression for the amount she has saved in terms of n. Well, again, this should be pretty easy if you look at the calculation we did over here, right? In this case, literally n was equal to 12, right? So, right, instead of having n equals 12, we just want to leave the n all by itself. So the phrase, or the expression that's going to calculate how much she saved is 20 times the number of weeks, because she's saving $20 per week, plus that $60 she started with. So now, if you gave me a certain number of weeks, if you said, well, what about after, 30 weeks? Well, I could put 30 in here, evaluate the expression, and it would tell me, how much money she had saved up. It wouldn't tell me if she had saved up enough, then we'd have to compare it to the 400, but it would tell me how much she saved up. All right. Letter C, very easy. What is the smallest amount that Rosa wants to save? Well, that's really easy because that phrase that says she wants to save at least $400, well, means that the smallest amount that she could be saving is $400. Nothing more than that, right? That's it, $400. Now, letter D. Set up and solve an inequality that shows the values of n that Rosa could save to meet her goal, right? So, in other words, what are some weak values, like how many weeks, not weak as in I'm not very strong, but how many weeks, right, will it take her to save at least $400? Well, again, 400 means it could be 400, it could be 401, 402, $400.50, it could be $500, it could be $2,000. The plain fact is the phrase at least, right, at least translates into, is the same as greater than or equal to, right? That's what at least is. So our inequality is going to be 20n plus 60 is greater than or equal to 400, right? That's the inequality that models this problem, right? 20 times n plus 60, which is the amount of money she saved, must be greater than or equal to the minimum amount of money she wants, which is 400. Now, solving this is pretty easy, right? I'm just going to subtract 60 from both sides, and this is where, if you want, you could use your calculator. 20n must be greater than or equal to 340, right? Now I'm going to divide both sides by 20. And again, I can do this in my head, but if you need to use your calculator, feel free to do so. N is greater than or equal to 17, right? By the way, notice we never use that special property of inequalities where we flip the inequality because we didn't divide or multiply both sides of the inequality by a negative number, right? We subtracted 60 from both sides, but that's perfectly okay. And then we divided by 20 on both sides. That's also perfectly okay. Now, just for a moment, even though the question didn't ask this, think about what that really tells us. What that tells us is that Rosa could be saving money from 17 weeks on. So really, at 17 weeks, she saved her $400. But any time after 17 weeks or later or greater, right, she will have enough money to meet that $400 threshold. All right, awesome. I just keep moving that thing around. Let's keep going. Let's take a look at another problem. Exercise number 2. A truck can hold at most 750 pounds. It is loaded with a desk that weighs 125 pounds and boxes of books that weigh 15 pounds each. Letter A, could the truck hold 48 boxes of books along with the 125-pound desk? All right, great. Well, why don't you go ahead and pause the video and see if using all the information they gave in the problem, the truck could hold 48 boxes of books and a 125-pound desk. Go ahead and pause the video. Well, let's see how much weight the truck is holding with 48 boxes and a 125-pound desk. Now, one thing that we know is that the books weigh 15 pounds each. There's a rate, right? It's not really written as a rate, but it's really 15 pounds per book, right? 15 pounds each. All right, so what would I do? Well, I would take my 15 pounds and I'd multiply it by the number of books I had, 48. Then, of course, I'd have to add in my 125-pound desk. I'm going to use my calculator to help me out here. All right, I'm going to do 15 times 48. I could do this all at once on the calculator, but first I think I'm going to have my 720 plus 125. And that's 845 pounds. Now, keep in mind, right, that the problem tells me that the truck can hold at most 750 pounds, which means it must hold 750 or fewer pounds. 845 is too large, right? At most it can hold 750. So the answer is no, right? the truck cannot hold 48 boxes of books and a 125-pound desk. Now, side note, right? If the 125-pound desk wasn't on there, you'd be fine because you'd have 720 pounds worth of books, and that's less than our 750. So we'd be good to go. Let's take a look at letter B. Let B represent the number of boxes loaded. Write an inequality that models all possible values of B. Solve the inequality. All right. Let's take a look at this. Now again, right, let's model this inequality. First, let's just write down an expression that models the amount of weight that's being held in this truck based on the number of books, B, that we put in there. Well, how do we calculate the amount of weight? We take the weight per box, which is 15 pounds, we multiply it by the number of boxes, which isn't going to be 48 this time, it's going to be just the variable B, and then we add on 125 pounds for the desk. So what does that look like? That looks like 15B plus 125. So that is simply, that's not an inequality obviously, that is simply an expression that predicts the amount of weight that's on the truck. We want to hold at most 750 pounds. That means 750 and less, or less, I suppose. So the inequality would be less than or equal to 750. In fact, that phrase, at most, right, almost always translates to a less than or equal. Let's solve it, right? Nice two-step inequality. Let's subtract 125 from both sides. That's going to give me 15 times B is less than or equal to 625. No need for a calculator there. But this time I think I'm going to want my calculator. Let's take this thing out, clear it, and do 625 divided by 15. And looks like we got a repeating decimal there, so it looks like 41.6 with the 6 repeated. All right, there it is, right? That is the solution to the inequality. Now that might seem a little funny to you, especially because it's got a decimal. But that's where letter C comes into this problem, right? Letter C. What is the largest whole number of boxes that can be loaded onto the truck? So the idea here, right, is that we're loading these boxes on, right? We can't load a fraction of a box. We can't have 41.6 boxes, right? So what is the largest number of boxes that we could possibly put on the truck? Remember, we've also got that 125-pound desk. Pause the video now, and what do you think is the answer to letter C? Well, this can be a little tricky, because for some kids, they might look at 41.6 repeated, and they might say, well, that rounds up to 42. And certainly the number 41.6 would round up to 42, except the number of boxes that can be loaded onto this truck must be less than or equal to 41.6, which means the largest whole number of boxes that could be on the truck would be 41. You see, 42 would be greater than 41.6, right? So I can't load 42 boxes onto the truck, but I can get 41 on there. All right, let's do another one. A little geometry going on now. Exercise number 3. Owen is designing a rectangular garden whose length is 25 feet. He needs to put fencing all around the exterior of the garden and wants to use less than 80 feet of fencing. All right. Letter A, could the garden have a width of 12 feet? Show the calculations you used to find your answer. All right, awesome. I mean, what do I know about this, right? I know I'm going to put fencing up around the, the perimeter of this rectangle. Okay. And my question is, well, could the width be 12 feet if the length is 25 feet? Pause the video now and see if that could be the width. That's pretty simple, right? I mean, if the width is 12, right, we'd have a 12 here, a 25 here, and another 12 here. So what would we have? We'd have 2 times 12 plus 2 times 25. 2 times 12 would be 24 feet. 2 times 25 would be 50. That would give us 74 feet. And, well, we want to use less than 80 feet of fencing, so sure, yes. Right? The width could be 12 feet. All right, it could be a lot of other answers as well, but it could certainly be 12 feet because we end up using less than 80 feet. And who knows, maybe it was because we went out and we got a roll of fencing that was exactly 80 feet long, in which case it would probably be less than or equal to 80 feet, but whatever. Let's keep going. Letter B. Let W be the width of the garden. Set up and solve an inequality for all possible values of W. On top of that, we're then going to give an interpretation of our answer. Well, see now if you can model this problem based on the fact that W stands for the width and we want to use less than 80 feet of fencing. Pause the video now and see if you can model this problem and solve the model. All right, well first let's write down an expression that simply tells us how much fencing we use. Well, we're going to have two W's. Right? That's what we had up here when we had 2 times 12. But we're also going to have plus 2 25s. That's non-negotiable, right? So this expression, 2 times W plus 2 times 25, literally tells us how much fencing we use if we're given a value of W. Now we know that that amount of fencing, that entire phrase, right, that entire expression, must be less than 80 feet because we were told we want to use less than 80 feet of fencing. So now we can solve it, right? Now we probably want to do something like take the 2 times 25 and make it into 50. All right, but now, real nice kind of just two-step inequality. All right, we'll get 2W is less than 30. Now I will divide both sides by 2, and W is less than 15. All right, that's it. Again, that special property of inequalities where we divide or multiply both sides by a negative, therefore flipping the inequality, that never came into play on this. Now what's really cool is there's a great interpretation of this answer. Literally, what does this tell us? Think about that for a moment. Well, it tells us that the width of the rectangle must be less than 15 feet. You know, if we want to use less than 80 feet of fencing, and we know that the length of this rectangle is 25 feet. Maybe we need it to be 25 feet because, you know, we want to plant rows in the garden that are 25 feet long or something like that. Who knows, right? But this answer then tells us the width must be less. Whoops, not than 25. It certainly has to be less than 25 feet, but it must be less than 15 feet. Yeah. And it's great. All of these things really do have a nice interpretation. You know, the last one that we had, you know, the number of boxes had to be less than 41.6 repeated. Well, you know, really that means that we could have 41 or 40 or 39, etc. boxes on that truck without exceeding the weight limit. All right, let's take a look at one more problem. Now, remember that special inequality property. Be mindful that if we divide or multiply both sides of an inequality by a negative, then we have to switch the direction of the inequality. And yes, this can actually come up in real life problems. So let's take a look at how that plays out in exercise number 4. An elevator in an apartment building starts 330 feet above the ground. It moves down at a rate of 8 feet per second. Look at that rate. We are interested in finding all times t when the elevator is above 200 feet. All right, so let's talk about the context of this problem a little bit, right? If you live in a big city, you know, or if you've ever been into a big apartment building or just a, you know, a high rise or something like that, you know, you're way up, right? Maybe you're on the 25th floor or the 38th floor or something like that, and you get into an elevator. You're 330 feet above the ground and you start going down. Maybe it's even one of those cool buildings where you can like see the skyline by looking out of the elevator, but maybe your view is blocked if you drop below 200 feet because there's other buildings or something like that. So maybe you're just interested in how long, you know, like what times you can still be above the 200 feet. All right, so you understand the context. All right, given that you're dropping what? 8 feet per second. You're moving down 8 feet per second. So letter A asks, will the elevator be above 200 feet after dropping for 12 seconds? All right, I'd like you to play around with that just to see if it will be. And then as well, right away, do also letter B. Will the elevator be above 200 feet after dropping for 20 seconds? Play around with those two. Well, how would we figure this out? Well, for 12 seconds, the first thing we might just do is figure out how far the elevator has dropped. So maybe I'll just write it as dropped. Right? It's dropped. Right? We've got 8 feet per second, 12 seconds. So we're going to do 8 times 12. Again, maybe just bring this out real quick so I don't have to think about that too hard in my head. I almost can't help think about it. It's 96. Right? So that's the number of feet it's dropped. But where is it actually? Well, it's 330 minus how many feet it's dropped. So now we've got 330 minus 96, and we get 234. So is it above 200 feet? And the answer is yes. All right. So after 12 seconds, the elevator is still above 200 feet. But now let's take a look after 20 seconds. Same calculations, right? First thing I might want to do is just figure out how far it's dropped. So, right, it's dropped in those 20 seconds by 8 feet per second times 20 seconds. This one I can do in my head. It's dropped 160 feet. So where it's actually at will be 330 minus 160. So 330 minus 160. It's at 170 feet. So no, right? And it kind of makes sense that, like, right, I mean, if you're 330 feet above the ground and you start dropping at 8 feet per second, right? In the early times, you're going to be above 200 feet, right? But eventually, you'll hit 200 feet and then you'll pass below it. That's got to happen sometime between 12 seconds, where we're above 200 feet, and 20 seconds, where we're below 200 feet. And obviously, that's what we're going to be figuring out in letter C. Now let's take a look at that. Letter C. Let t equal the amount of time in seconds the elevator has been dropping. Set up and solve an inequality involving t for the times when the elevator is above 200 feet. Well, again, let's just do it like step by step the way we did it before. First, how far has it dropped? Right? So instead of having an actual time in there, now I just have t, right? And how did we figure out how far it had dropped before? We kept doing 8 feet per second times the amount of time it was dropping. 8 feet per second times the amount of time it's been dropping. So it has dropped 8 times t. Simple enough. Now, where's it at, right? Where it's at, then, we always calculated by doing 330 minus how far it's dropped, because we started it at 330, right? Now, we want to know when where we're at is above 200 feet. Well, it should come as no surprise, right, that then leads to this inequality. So this is the inequality that is going to model the question that we're trying to answer. What are the times when we're above 200 feet? But now we have to solve it. All right. Now, again, like in many cases, we're going to take a look at the left-hand side of this inequality, and we're going to use the commutative property of addition to actually kind of rewrite the left-hand side as negative 8t plus 300 is greater than 200. All right. Simple enough. Okay. Now I'm going to subtract 300 from both sides. Got to watch out a little bit here. We'll be left with negative 8t is greater than 200 minus 300 is negative 100. No issue there, but here comes that property of inequalities. I'm going to divide both sides by negative 8. Now, as soon as I do that, I have to switch that greater than symbol to a less than symbol. All right, now maybe I want to bring my calculator out so I can do negative 100 divided by negative 8, and I find that t is less than 12.5 seconds. Now, think about this just for a moment, right? What this says is that if I get on this elevator, right, 330 feet going down at 8 feet per second, then for all times less than 12.5 seconds when I'm on the elevator, I'm going to be above 200 feet. So anytime I'm on the elevator less than 12.5 seconds, I'm still above that 200 feet. Well, take a look. Will the elevator be above 200 feet when it's been dropping for 12 seconds? Keep in mind, 12 seconds is less than 12.5 seconds. And the answer was yes. I wasn't much above 200 feet, but I was above 200 feet, right? Now, on the other hand, when I hit 20 seconds, then what happened was I was well below, right? I was well below that distance. Now, I'm just noticing something right now. I've made like a small mistake here, although it's a big enough mistake that we should go back and correct it. Somehow, a 330 here became a 300 over here. I don't know. So that 12.5 is wrong. Let me just go back and correct this work real quick. It'll just take me a moment. That should have been 330. 330 doesn't magically change into 300 except in Kirk world, which just sometimes happens. All right. So I'm going to get 200 minus 330, which is negative 130. But everything else is going to stay the same except that negative 130 divided by negative 8 is not going to be 12.5. It's going to be 16.25. So let's change that a bit. All right. All right. Same analysis though, right? Now for any moment in time that is less than 16 and a quarter or 16.25 seconds, we're going to be above that 200 feet elevation. And once we get by our 16 and a quarter seconds, i.e., let's say 20 seconds, now we're going to be below. All right. And this is a great example of where that property, that special property of inequality comes into, right? Because we're forced to divide both sides by the negative here, and that greater than 200 suddenly becomes a less than 16.25. All right, let's wrap this lesson up. So, what we saw today were many situations where we could model real-life problems based on inequality work. You're looking for phrases like at least, at most, more than, less than, below, above. Things like that are indicating that you've got inequalities instead of equalities going on. And really, when we model those and we solve them, it's really not very different than when we were modeling word problems with two-step equations. Probably the biggest difference, right, is deciding on which way the inequality goes and then watching for those special situations where we might divide both sides by a negative. Again, that's not going to happen often, but it could happen, and it certainly will probably be something that you'll be asked about on some test or exam or whatnot. Anyway, for now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.